Let us understand the Earth's magnetism. At the center of the Earth is the Earth's core. It is made from iron and nickel and is divided into two parts. The inner core is made of solid metal and the outer core is made of liquid metal. As the Earth spins, the two parts of the core move at different speeds, and this is thought to generate the magnetic field around the Earth, which is known as the dynamo effect. The Earth spins on its axis, which is imaginary line that runs through the center of the planet. The ends of the line are called the geographic north and south poles. Their positions on the surface of the Earth are fixed. The north magnetic pole is the place to which the north poles of bar magnet points. In reality, it is the Earth's south magnetic pole because it attracts the north poles of the magnets. Similarly, the south magnetic pole is really the Earth's north magnetic pole because it attracts the south poles of bar magnets. However, for most purposes, the old and incorrect names for the magnetic poles are still used. The magnetic lines of the Earth resemble that of a hypothetical magnetic dipole located at the center of the Earth. The axis of dipole does not coincide with the axis of rotation of Earth, but it is tilted by approximately 11.3 degree. The location of the north magnetic pole is at a latitude of 79.74 degree north and longitude of 71.8 degree west, a place somewhere near North Canada. The magnetic south pole is at 79.74 degrees south and 108.33 degree east in the Antarctica. The pole near the geographic north pole of the Earth is called the north magnetic pole, and the pole near the geographic south pole is called the south magnetic pole. There is some confusion in the nomenclature of the poles. If one looks at the magnetic field lines of the Earth, one sees that unlike in the case of a bar magnet, the field lines go into the Earth at the north magnetic pole and come out from the south magnetic pole. The convention arose because the magnetic north was the direction to which the north pole of a magnetic needle pointed. The north pole of a magnet was so named as it was the north-seeking pole. Thus, in reality, the north magnetic pole behaves like the south pole of a bar magnet inside the Earth and vice versa. Example: what is the magnitude of equatorial and axial fields due to a bar magnet of length 5 cm at a distance of 50 cm from its midpoint? The magnetic moment of the bar magnet is given to be equal to 0.4 ampere meter square. Solution: BE equals mu naught m divided by 4 pi r cube. So putting the values, we get the result as 3.2 into 10 to the power minus 7 Tesla. And BA is equal to mu naught into 2m divided by 4 pi r cube, which is equal to 6.4 into 10 to the power minus 7 Tesla. Example: the figure below shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. The other arrows show different positions and orientations of the magnetic moment of another identical magnetized needle Q. A. In which configuration the system is not in equilibrium. B. In which configuration is the system in 1. Stable and 2. Unstable equilibrium. C. Which configuration corresponds to the lowest potential energy among all the configurations shown? Solution. Potential energy of the configuration arises due to the potential energy of one dipole, say Q, in the magnetic field due to the other, say P. Use the result that the field due to P is given by the expression BE equals minus mu naught m by 4 pi r cube and BA equals mu naught into 2m divided by 4 pi r cube, where MP is the magnetic moment of the dipole P. Equilibrium is stable when MQ is parallel to BP and unstable when it is antiparallel to BP. For instance, for the configuration Q3, for which Q is along the perpendicular bisector of the dipole P, the magnetic moment of Q is parallel to the magnetic field at the position 3. Hence, Q3 is stable. Thus, the following are the answers. Concepts. Question 1. Magnetic field lines show the direction at every point along which a small magnetized needle aligns. Do the magnetic field lines also represent the lines of force on a moving charged particle at every point? Solution. No. The magnetic force is always normal. Remember, magnetic force is Q V cross B. It is misleading to call magnetic field lines as lines of force. Number 2. Magnetic field lines can be entirely confined within the core of a toroid, but not within a straight solenoid. Why? Solution. If field lines were entirely confined between two ends of a straight solenoid, the flux through the cross section at each end would be non-zero. But the flux of the field B through any closed surface must always be zero. For a toroid, this difficulty is absent because it has no ends. Number 3. Does a bar magnet exert a torque on itself due to its own field? Does one element of a current carrying wire exert a force on another element of the same wire? Solution. No. There is no force or torque on an element due to the field produced by that element itself. But there is a force or torque on an element of the same wire. For the special case of a straight wire, this force is zero. Question 4. Magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is zero? Solution. Yes. The average of the charge in the system may be zero. Yet, the mean of the magnetic moments due to various current loops may not be zero. We will come across such examples in connection with paramagnetic material where atoms have net dipole moment though their net charge is zero. Let's understand magnetic declination and dip. Consider a point on the Earth's surface and place a compass there. At such point, the direction of the longitude determines the geographic north and south directions. The vertical plane containing the longitude circle and the axis of rotation of the Earth is called the geographic meridian. The magnetic needle, which is free to swing horizontally, lies in the magnetic meridian with its needle pointing towards the magnetic north and south poles. Since the line joining the magnetic poles is tilted with respect to the geographic axis of the Earth, the magnetic meridian at a point makes angle with the geographic meridian. The angle formed between the true geographic north and the magnetic north is called magnetic declination or simply declination. This declination is greater at higher altitudes and smaller near the equator. In India, declination is small, that is 0 degree 41 minutes east at Delhi and 0 degree 58 minutes west at Mumbai. Thus, at both these places, a magnetic needle shows the true north quite accurately. Angle of dip. There is one more quantity of interest. If a magnetic needle is perfectly balanced about a horizontal axis so that it can swing in a plane of the magnetic meridian, the needle would make an angle with the horizontal. This is known as the angle of dip, also known as inclination. Dip is the angle that the total magnetic field BE of the Earth makes with the surface of the Earth. The figure shows the magnetic meridian plane at a point P on the surface of the Earth. The plane is a section through the Earth. The total magnetic field at P can be resolved into a horizontal component HE and a vertical component ZE. The angle that BE makes with HE is the angle of dip. To describe the magnetic field of the Earth at a point on its surface, we need to specify three quantities. They are the declination, the angle of dip or the inclination, and the horizontal component of the Earth's field. These are known as the elements of the Earth's magnetic field. Representing the vertical component by ZE, we have ZE equals BE sin I and HE equals BE cos I, which gives tan I equals ZE by HE. Example: in the magnetic meridian of a certain place, the horizontal component of the Earth's magnetic field is 0.26 and the dip angle is 60 degree. What is the magnetic field of the Earth at this location? Solution: it is given that HE is 0.26. From the figure shown, we have cos 60 degree is equal to HE by BE. So, BE is equal to HE by cos 60 degree, which comes out to be equal to 0.52. Concepts. Number 1. What is the angle of declination? Solution: the angle between the geometric meridian and magnetic meridian is called angle of dip. Question 2. What is the angle of dip? Solution: the angle between horizontal component of Earth's magnetic field and resultant magnetic field is called the angle of dip. Question 3. What will be the angle of dip at the poles? Solution: the angle of dip at the poles is 90 degrees since there is no horizontal component of Earth's magnetic field at the poles.